In this video I'm going to continue looking at the oblique plane and this time at spatial coordinates. So spatial coordinates is similar to what you encounter in maths in coordinate geometry, where you have an x and a y value. Here we're adding a third axis, the z-axis, as you're familiar with from SolidWorks. So I'm just going to have a quick look in our SolidWorks model. And if you look down in the bottom right hand corner of the screen there, it says trimetric, and you can see the three axes. You can see the x, y and z axis. So x axis is going to be a horizontal distance from left to right, y will be a vertical distance, and z would be the distance out from the wall. So what I'm referring to there is, if we look at a question, so this is one of the Leaving Cert questions, we're given coordinates for each of the points A through F. So for A, we're told that it's 205, 0 and 40, and that is an x, y and z value. So that means that the x value for A is 205, so that's measuring in 205 millimeters from our start point on the left. The second value, 0, that's the y value, so that is how high off the horizontal plane it is. In this case it's sitting on the horizontal plane. And finally, the 40, that's the z-axis, that's how far out from the vertical plane that point is. So if I look in our question in our book, we have got this lamina here, and we are given 3 points A, B and C. Now we're given different bits of information. We are told that point A is 45 millimeters. So point A, if I highlight point A, is this one. And we are given 3 values for that. So point A is 45, 30 and 60. So that means in the front view, the elevation, it is 45 millimeters from our origin on the left. The next value is its altitude, how high it is off the ground, and it's 30 millimeters, and you can see that in the picture on the right, top right. And then in the bottom left image, you can see the z value, which is 60. So that's how far out down from the xy line it is. So our first value, x, is the distance in from the left. Our second value is its altitude above the horizontal plane, and our third value is how far it is down or out from our wall, so how far we'll measure down from our xy line. The same thing applies to B. So point B is the top one, is this one up here. So B has an x value of 96. It has a y value of 63, so it's 63 millimeters up off the ground, and it has a z value of 12, so it's 12 millimeters out from the vertical plane, which we can see in the top right corner of our screen. And then C, we're also given the coordinates for that. So how do we go about drawing that on our page? So we'll just have a look at doing that now. So we are given 3 coordinates for A, B and C. So for A, we're told we're going to need a reference line, a datum line, and that's where we're going to measure from. That would be our origin in SolidWorks. So we're going to measure in from the from that. For point A is going to be in 45 millimeters. And it has an altitude, we're told, of 30. So that's the height, we can see that height here. And it has a distance out from the back, from the vertical plane of 60. So that's point A. Point B, now we're told, has a distance of 30 millimeters in our x value, 30. It has an altitude, B has an altitude, distance of 96, sorry. So B is in 96, has an altitude of 63, is B, and a distance out from the wall of 12. So this is 12, and that's B. And C finally has a distance of 114. Has an altitude of 9 millimeters and a distance out from the vertical plane of 30. So this is C and C. So I've just zoomed in a little bit there. So once we've located each of our points, we're now able to join all the points up to form the lamina. So A, B, and C all join together. So this is the lamina in plan. And this is it in elevation. So just a quick recap on what we've done there. We have our datum line, our reference line where everything is measured from. Each point A, B, and C are given an X, Y, and Z coordinate. The X value is the distance left to right, so how far we're measuring in from our point here. Our second value will be its altitude above the horizontal plane, so how high up it is going to be, and we can see that in the elevation. And then the final value is the distance out from our vertical plane, so we'll see that in the plan. So we have three values: the distance in from our reference point, our altitude, and the distance out from the back wall from a vertical plane. The next part that we're going to look at here is how we might find an edge view of the plane. So to find an edge view of the plane, what we're going to do is we're going to find a true length line on the surface of it, because if we find a true length of that line and get a point view of it, one of our key principles of DCG is that if you find a point view of a line on a surface, you find an edge view of that surface. So we're going to find a true length line, and then by finding that true length line, we'll get a point view of it. So what I'm going to do is I'm going to draw a horizontal line in the elevation. And the reason I'm drawing a horizontal line is that if I have a horizontal line in one view, in the other view, so if I have a horizontal line in the elevation, it will be a true length in plan. Again, if I had a horizontal line in plan, it would give me a true length in the elevation, because I'm looking perpendicular at it. So in my elevation, I am going to draw a horizontal line, and I'm going to pick point A as my starting point, as it's in the middle, and if I draw my horizontal line, it'll intersect the line BC. So this is a horizontal line. I need to find that same line now down in plan. So I'm going to project this down, the end point of where it intersects the line BC, down until it intersects the same line BC down in plan. It started at A, it ends at this point, so it starts at A, ends at that point, so it's going to start at A and end at the same point in plan. This line down here now is a true length, because it is horizontal up here, and now when I'm looking down on top of it, I'm looking perpendicular to that line. So this is a true length. So if I now have a true length of that line, what I can do to find an edge view or a point view of that line is I'm going to look along that line. So looking along that line, use my two set squares together, and I extend the true length line out along here. I draw in an x1, y1 line. So the x1, y1 line is perpendicular to the true length line. And each of my other points I'm going to project out along here also. So taking my true length line, projecting each point out, C and B. And each one of these points is going to have the same altitude as this is an auxiliary elevation. my points, the heights can be taken from this elevation up here. So point A has an altitude, we're told, of 30, so I can either measure it up with my compass or measure it with the set squares. Altitude of 30, and I'm going to mark that up from my x1, y1 line, and this is going to be point A. It is also the horizontal line, a point view of that horizontal line. B, again measuring this, or measuring, just copying the distance and marking that up here. So it's an altitude of 63, and C then also, which had an altitude of 9, that is marked down here. So this is B and point C down here. Now each of these lines should then join up and form a single line. So this gives me an edge view of that surface. So just label and get the height C here. This height is taken from C in the elevation. So following our standard rules of auxiliary views, if I'm using this view, I'm skipping this one, measuring from this one. So taking here, skipping one, going back to the next one. So just a quick recap on what we've done here. After locating each of the points, I take a horizontal line on the surface. So this is horizontal. In plan, that is going to give me a true length. And if I look along a true length line and find a point view of it, which is on a plane, I will find an edge view of that plane. This is going to be a very useful piece of information, not only for the oblique plane, but later on when we start looking at geologic geometry, this is going to come up again.